Welcome to Mark's Tech Talk. In this edition, we're going to explore converting from circuit diagrams to Boolean expressions and vice versa. So first thing to do is to look at the logic gates and understand how they are related to Boolean expressions. First thing we have is an AND gate. That is equivalent to Boolean multiplication. And remember, multiplication may or may not be depicted with a dot. Sometimes we just have the letters adjacent to each other to indicate multiplication. The NAND function is very similar, A ANDed with B, but this time we invert it, and we indicate inversion in Boolean by putting an overbar over the top of the expression. Here we have an OR gate. Notice the expression is addition, so the Boolean equivalent to an OR gate is addition. And then if we want to do a NOR gate, we have to invert the addition, so we put an overbar there. The exclusive OR is indicated by an addition, but with a circle around the plus sign. It's kind of a special symbol that you probably won't run into other places. And then the exclusive NOR, very, very similar. The addition with a circle around the plus sign, and then the overbar to indicate the inversion. It's important to remember when we are utilizing these variables A and B, each of these can actually be combinations of other variables. For example, A might be C plus D and B might be EF, and then we get this expression, the C plus D ANDed with EF. So again, you're seeing combinations of expressions. And that's what we're going to do when we combine several gates from a circuit and get the Boolean expression, a larger Boolean expression. As an example, let's say we have A plus B times C. Well, remember the multiplication is the Boolean and one input will be A plus B, the other input would be C. So now we have to add an OR gate in order to get that A plus B, and there it is. So that is how we would create that expression using our logic gates. Okay, let's look at another one, A plus B plus C plus D. Well, first of all, we're doing an OR function, and we could input A plus B on one and C plus D on the other, and get each of those by an OR function. This one actually was probably the long way around because it turns out there are OR gates available with 4 inputs. So we can do this with a 4 input OR gate if we chose. That'd be another way to do that. Here's another expression, A plus B plus CD. So we're going to OR everything together, and one input will be A plus B, the other is CD. So the A plus B would be an OR gate, and the CD would be an AND gate. So there it is. That's the circuit that creates that expression. Here's another one, A plus B plus CD. Again, A plus B can be on one input, or we can actually use a third input on the OR gate. Either way, we can implement that. So it's just an alternative way of implementing that expression. Now we'll look at using the overbars. We have A plus B plus CD and an overbar over everything. So our overall function there is the addition with the overbar, so that would be a NOR gate. So the first input to the NOR would be A plus B, the next one would be CD. So A plus B would be an OR gate, and then CD is an AND. So you just sketch that out, and there you go. Here we go with a couple of overbars. We have A plus B plus not CD, and then overbar over everything. So the overbar over everything along with the addition gives us a NOR gate, and then one input is A plus B and the other one is not CD. So A plus B and not CD, well, the A plus B is simply an OR gate, and the not CD is a NAND gate. So there it is. That's how you sketch it out. Here we have another NOR gate and another overbar, and then notice we have the exclusive OR between A and B. So first of all, we start with a NOR, and then first input would be A exclusive ORed with B, and the second input would be CD. So there's the two inputs. Well, the first one, of course, is simply an exclusive OR, and the CD is an AND gate. So it's just that simple. All right, how about if we want to go the other way? If we have the circuit and we want the expression, notice we have an AND gate. That would be multiplication. So we have AB, and then C just passes directly through. It doesn't go through any gates. And then those two expressions are ORed together. So we have AB plus C. And here's another one. First of all, we have to invert the A, and then the A and B are ORed together, and then the C and D are going to be exclusive ORed. And then we have to do a NAND function at the end, so multiplication with the overbar. And that gives us this expression. So hopefully that will, there's enough examples to give you an idea of how to convert back and forth between digital circuit diagrams and Boolean expressions. Hope you enjoyed this edition of Mark's Tech Talk. Stay tuned for other videos in the series. Thanks for watching.